Welcome, everyone. It's my pleasure today to introduce our guest speaker, Guangshuan Xiao. He is a third-year PhD candidate at MIT in the EECS department, where he's advised by Professor Song Han. He focuses on creating efficient algorithms for deep learning, especially for large language models. His work has earned widespread attention and made a tangible impact on industry practices. His key contributions include smoothquant and streaming LLM, both of which have been widely adopted and integrated into platforms such as NVIDIA's TensorRT LLM, Hugging Face, and Intel's Neural Compressor. With that, I will hand it over to Guangshan. Okay.
Okay, thank Professor Naik for having me today. And hi, everyone. I'm Guangshan Xiao, a third-year PhD candidate at MIT, advised by Professor Song Han. So today, I'm very happy to introduce a series of works in our lab on efficient deployment of large language models. So today, I will focus on a very crucial technique called quantization. And the goal of this lecture is to understand how quantization can reduce the model size and also improve the computational efficiency. And we will explore, we will start from the basic concept of quantization, and from basic, and we move to some advanced techniques like smoothquant, AWQ, and our recent research, QSERV. So before we dive into the quantization, let's just go over some basic background. So as we may hear constantly, large language models powered by the transformer architecture shown in the figure on the left, such as OpenAI GPT-4, they revolutionized the field of natural language processing and also artificial intelligence. And people train these models on massive text data, and they're able to generate contextually relevant and highly accurate responses. And the potential of large language models extends far beyond the chatbots like ChatGPT. They also play a very crucial role in other high-impact fields, such as protein language models for scientific discovery, and Copilot that can speed up software development, and AI assistant designed to support individuals with disabilities. And behind these cool applications is the scaling law and emergent abilities of large language models. The scaling law describes the relationship between the model size, training data, and the performance. As we increase the size of language model and provide it with more training data, we observe improvements in performance and the emergence of some new, sometimes surprising abilities. And this phenomenon is the key driving force of people ongoing trend of developing even larger language models as we strive to unlock some new and unforeseen applications that can benefit us. However, as the size and the computational requirements of large language models increase exponentially, there emerges a significant gap between the capability of hardware accelerators and the demands of these massive models. As shown in this figure, model sizes increases at dramatically faster rate than the GPU memory where people run the models on. So addressing these issues are crucial, and efficient deployment algorithms such as model compression and quantization techniques play a vital role in bridging this gap. And as we all know, serving large language models can be extremely expensive, as evidenced by the challenges faced by ChatGPT in its initial months. ChatGPT was constantly at capacity and temporarily paused on upgrades to ChatGPT Plus accounts due to the overwhelming demand. So today I'm going to introduce very widely used, it's an industrial standard method called quantization to address these methods. So here is the agenda of what we are going to cover today. So first we will go over the basics of linear quantization, and then we will look at weight and activation quantization using smoothquant, and followed by the weight-only quantization methods such as AWQ and TinyChat, which is very useful in edge cases. And last, we will discuss more advanced optimization strategy we recently developed, combining the benefit of smoothquant and AWQ, which is called QSERV. So let's dive into linear quantization. So before diving into linear quantization, let's just introduce what is quantization. So quantization is it's a very old concept in digital signal processing. So here is a definition from Wikipedia. quantization is the process of constraining an input from continuous or otherwise large sets of values to discrete sizes. So in the figure on the left, we are representing a continuous signal, which is like a sinuous wave into discrete values, which is represented by the yellow dots. And also we can observe that there are some quantization error observed, which is represented by the red segments. And it also widely used in our daily lives. For example, if we want to compress an image, we use a technique called quantization. We also use quantization because we discretize these color levels and map them into smaller sets. And in neural networks, everything is matrices. So let's start with an example to understand what is linear quantization. So here is a higher precision weights represented by 32 bits floating point numbers. And here is the final result of how we can use quantization to compress this matrix. So in the middle, we use we have the 2-bit quantized weights. So in this matrix, we only have -1, -2, 0, and -1, only 4 values. So we are using actually 2 bits to represent original 32-bit matrix. And in this approximation, we need several quantization configuration, so which is the 0-point n scale. So the 0 point here is actually the offset of the quantized weights. So the equation will be the quantized weights minus 0 point multiplied by a floating point scale, which is the reconstruction weight. Also, we can observe that the reconstructed weights is not equal to the original weights. So there is a quantization error, which is shown on the bottom right. It's the difference between the original weights and the reconstructed weights. And actually, linear quantization is the simplest method of quantizing continuous data. So we just do a fine mapping of integer to real numbers. So which is represented by this equation. We use an integer q to approximate the original continuous floating point number r, and by using two quantization parameter, 0 z and floating point s. So the 0 z actually represents which value in this integer range represent the original 0 point in the R. So if we take Q equals to 0, then we can get R equals to 0. And the floating point represent actually the step size of quantization. So how long is one step size in this quantized range represents the original floating point range. So here is another illustration of how quantization works. So we map the quantized range Q minimum to Q maximum to represent the original floating point range R minimum and R maximum, and the z value, which is the 0 point, represents the original 0 point of the floating point range. And we also, for different quantization configurations, which is the bit width. For example, sometimes we can quantize it into lower bits, but sometimes we have to keep it into higher bits because of the quantization error. So for example, if we can quantize the values in 2 bits, then the Q minimum equals to -2 and the Q maximum equals to 1. And if we quantize it in 4-bit, the Q minimum is -8 and Q maximum is 7. And in general, the Q minimum equals to -2 to the power of n minus 1. And the Q maximum equals to 2 to the power of n minus 1 minus 1. And so since this Q minimum and Q maximums are given, and R minimum and R maximum are given, so now how can we get these quantization parameters like Z and S? So we can derive it with two formula. So we get the relationship between R max, Q max, and R min and Q min by these two equations. And we can easily derive the equation for S by combining these two equations, which is S equals to R max minus R min over Q max minus Q min. And now so in this case, in this example, we have S equals to 1.07, which is because we get the maximum value in the original range and the minimum value in the original range, and which is 2.12 minus negative 1.08, and we divided by the total quantization range, which is 1 minus -2, and we get 1.07. And since we already get the quantization scale S, and we can substitute it into any of the equation we shown. So we substitute it in the relationship between R min and Q min, so we can get the 0 point, which is Q minimum minus R minimum over S. So since Q minimum is an integer value, so we have to do a rounding. So we do a round to nearest operation to the floating point 0 to get the final 0 point in the integer range. So in this example, we will substitute the minimum value in the matrix, which is negative 1.08, and we minus the we divide it by the scale we just got, and which is 1.07, and we get the final 0 point, which is -1. So that's how quantization works. That's very simple, right? So we just map the discrete range into original continuous range. So let's see how can we do linear quantized matrix multiplication, because basically all operations in neural networks are matrix multiplication, and we want to understand how quantization can accelerate matrix multiplication. So originally, let's consider this as the example we use in neural network, where we have a weight, which is W, multiply X, which is the input, we get the output Y. So let's assume they are in floating point numbers. Now we want to use quantization to accelerate this process. And we substitute them with the equation we get before. So here is the quantized version of the matrix multiplication. And we can organize this equation by taking out the quantized output in the left, which is Qy equals to some scaling factor multiply to quantized matrix and plus a bias, which is Zy. And we want to further organize this formula by taking out the Qw and Qx and make them together, because we want to use integer matrix multiplication kernels to accelerate matrix multiplication. So we organize the formula as shown above, below here. So we can see that Qy equals to some scaling factor multiply a quantized matrix multiplication subtracted by several quantized integers plus a 0 point number. And here in this parenthesis, we have a integer matrix multiplication followed by 32-bit integer addition and subtractions. Why 32-bit is because in GPUs, people always use higher precision integers to accumulate these numbers. So the output of matrix multiplications are always represented by higher precision, like int 32. And but this parenthesis is being multiplied by floating point numbers, and we don't want that to happen in our matrix multiplication kernel. So how can we avoid this? So in this equation, we can actually determine which scaling factor we use for the output. And that means we can determine the SY we used. So and followed by an offset. And we can actually determine which scaling factor of the output we use in this equation. So if we set this scaling factor by some value, then we can approximate this floating point scaling by integer operation, which is bit shift. So if we set this SW multiplied by SX over SY to some power of 2, then we can use bit shift operation to approximate this multiplication. And also we can, since the W is pre-known because it's a static weight, we can actually pre-compute the things colored, which is highlighted. So, and in real world, we have to compute the QW multiplied by QX, which is the integer matrix multiplication, minus a bias, which is ZW multiplied by QX, because QX is not pre-known. We have to compute it in runtime. But in real world, people sometimes set ZW equals to 0, which is the symmetric quantization. So if we go back to this slide, if we set z to 0, then we are actually using a symmetric range to represent the original range. So in this case, we are actually eliminating the second term in the parenthesis, which is zw multiplied by qx. Then that term does disappear because zw equals to 0. So I will pause for several minutes if people have questions in the linear quantization. Okay.
Error bound, since like you are kind of mapping a whole like continuous space into a discrete discrete form of like linear quantized result. Is there any like error bound guarantees on that?
Yeah, I think that's a very good question. So I think that's a very traditional research field in signal processing, which the error is actually determined by the input distribution. So different input distribution has different error bound. For example, if your continuous input is a normal distribution, then it has a bound. If it's another distribution, it has another bound. So in neural network, people didn't go that deep. So we just empirically approximate these and test the final end-to-end result, because in the end, neural networks are black box and we not understand them yet. So we just test the final output, and if the result is fine, then we just accept that quantization method. Yeah. Thank you. Yep.
That's when we update it every single time we're training the process.
Not training, inference. So yeah, because X is the input, we cannot know the input before inference, so we have to compute it on the fly. But for W, since it's a static weight, we can know it before doing the inference. So the term in highlighted can be pre-computed and merge into one term. Yeah. Okay, so I will continue. So let's move on to the next section, which is weight activation quantization method, smooth_quant. So here we already get some background on quantization. Let's more intuitively understand the benefits of quantization. So for example, when we serve a 175 billion parameter GPT-3 model, if we serve it people serve it in 16-bit floating point numbers, and the total model weights will be 350 gigabytes memory, which translates to 5 A100 GPUs. So if we can serve the model in 8-bit integers, now the minimum memory requirements will turn into 175 gigabytes of memory, and now we can serve it in 3 A100 GPU. So that's very intuitive, but we can actually, before smooth_quant, people can actually not use int8 weight and activation to quantize the model. So here is another background. In terms of activation, we are talking about the intermediate values running in the neural networks. So in neural networks, there are some weights which is already known, and they are putting there. But during forward passes, there will be some intermediate values multiplying by these weights. So we call these intermediate values as activations. So actually, before this work, quantization has already been an industrial standard in quantizing and deploying smaller neural networks like CNNs. So people are actually pushing this frontier to even lower bits. But why don't people use it on LLMs? Because quantizing large language model is especially difficult due to the outliers. And basically, this lecture will cover talking about outliers, because dealing with quantizing large language models is just dealing with outliers. And previous study find that when model sizes increase to a certain extent, for example, in this figure, when the model size increased to beyond 6.7 billion parameters in this figure, there will be systematic outliers emerge in the activations of those large language models instead of weights. So naive but efficient quantization method will destroy the accuracy. And I will dive into the outliers in the following slide. So here is sorry, I have to pause. Okay, here is a visualization of the activation matrices and the weight matrix in a large language model. So in these visualization, the color of the elements and the height of the elements indicates their absolute maximum absolute values, and we can actually see that their distribution is very interesting, and the activations are more challenging to quantize than weights because there are many outliers in the original activation matrix, and the weights are actually pretty flat and uniform. So previous works have found that quantizing the weights of LM with int8 or even 4-bit integers doesn't degrade the accuracy. So the quantization difficulty between activations and weights are not balanced. And secondly, we can see that outliers make the activation quantization difficult. The largest, we can focus on the largest value in the y-axis. The largest y-axis tick in this figure is 70. So we can see the magnitude of several, very few outliers actually is 100 times larger than most of the values. So remember, we are using 8-bit integer to quantize this matrix. So how many like intervals we have, how many levels we have in 8-bit integers? We have 256 levels, and for one side we have 128. So if the largest value is 100 times larger than most of the values, then we are actually only keeping the largest values, and we are flattening zero out all the values, almost all the values in the matrix. So that's why the outliers makes the activation destroy the model accuracy. So, but we have an observation which is very lucky for us. So we find that outliers persist in fixed channels. So we can see that there are a few channels. So the x-axis, this axis is the channel axis, and this axis is the token axis. We are feeding this language model the hundreds of tokens, 300s of tokens, and the hidden dimension of this model is 5,000, around 5,000. And we can see that actually outliers persist in fixed channels. So if a channel is an outlier channel, then across all tokens, this value will be very big. So and they persist in these activations because no matter how we change the input, the outliers will always persist there and be this channel. So it's actually give us two important messages. So if a model is already trained, we can detect which channels are outlier channels and address them. And secondly, since we are doing matrix multiplication of two matrices, the input activation and the weight matrix, the weight matrix W, if we do some mathematical equivalent transformation between these two matrices, the result of the matrix multiplication will not change. So here we can do a small experiment here. So if we multiply that huge channel in the activation by 0.1, and we multiply the corresponding column in the second weight by 10, then actually we are not changing the output of the matrix multiplication because matrix multiplication is linear. So by doing this, we are actually pushing down the quantization difficulty of the activation and rise up the quantization difficulty of weight, but make them quantizable by 8-bit integers. So here is the visualization after smooth quant. So we by migrating these scales from activations to weights, we can see that these outlier channels are hugely flattened, and this matrix are easier to quantize. But there are several small spikes emerge in the weights because we are migrating these scales into the following weights. So the weights are harder to quantize, but since we are still using 8-bit integers, these weight matrices are still easy to quantize and can be managed by 8-bit integers. And let's take a closer look about this process. So here is a toy example showing the inference in neural networks where we have input X, which is the activation, have several columns of outliers, which is in red and yellow. And we have a very flat and uniform weight matrix. And here is an example, one step-by-step example of showing how smooth quant work. So the first stage is the calibration stage, where we run several examples in the model and collect the distribution of the activations. So in large language models, we just run some random text into the model and collect how the activation look like. And we can see that there are two outlier channels, and we can collect the column-wise maximum absolute values, which is represented by max x, max the absolute value of x, and which is 2, 16, 2, 9. And we collect the row-wise maximum absolute value of the weight, which is max the absolute value of w, which is 2, 1, 2, 1. And after that, we divide these two vectors element-wise. So we divide max x by max w and get which is 2, 16, 2, 9, divide 2, 1, 2, 1, and we take a square root. So I will explain why square root. So we get 1, 4, 1, 4. This what we call is smoothing factor. So why we are taking square root? Because the general equation of the smooth point is shown below, and it's actually we have another hyperparameter alpha, which indicates the migration strength, how much quantization difficulty we are migrating from the activation to weights. And by setting the alpha as 0.5, we are actually halving the quantization difficulty between the weights and the activation, because we are setting the maximum absolute value to the same at each side. So in that case, that will be taking the square root. And I will use the square root as an illustration in these examples. And experiment also shows that 0.5 is a general sweet spot in the models we tested. And the second stage is a smoothing stage. So we already got the smoothing vector 1, 4, 1, 4, and we can smooth the model. So we, as you can see, if we do column-wise divide the input activation by this vector, we get a smooth activation, which is x hat 1 minus 2, 4, 2, 2, that matrix. And we have another. We also apply this smoothing process to weight, and we do a row-wise multiplication to the weights, and we get a slightly difficult to quantize but still easy by handleable by int8, which is w hat. So since can anyone see if there is any problem in this process? So in neural network inference, those activations are not pre-known. So we can actually not multiply this s to the x in neural network inference, because we don't know them beforehand. This process is doing offline. But how we can manage to do this is to change the output channel of the previous layer. So we can multiply this smoothing factor into the previous layer's output channel, and actually is absorbing this smoothing factor in the previous layer, so that we don't have to do a runtime column-wise vector matrix multiplication. Yeah, this is what we do in the model. So we actually multiply the previous layer's output by this smoothing factor, and multiply this, divide the previous layer's output and multiply this smoothing factor in the current layer's weights, so that these activations are automatically smooth at runtime. So here are the equations of this process. And then we deploy the model and quantize the model in 8-bit integers. As you can see, these outliers are hugely suppressed, and at runtime, they can be quantizable by 8-bit integer, and we can use int8 matrix multiplication kernels to accelerate inference. So here is an ablation study of the migration strength alpha. So we can actually do a sweep from 0 to 1. And as you can see that, as I mentioned before, setting it to 0.5 actually is a half the quantization difficulty between activations and weights. And setting this migration strength alpha to larger values, actually, we are migrating more quantization difficulty from weights to activation. So it will cause weights hard to quantize, but activation easy to quantize. And in this figure, all the weight quantization settings, such as the W8A16 and W8A8 settings, the green line and the red line all fail when we increase the migration strength alpha. And while we are decreasing the migration strength alpha, we're actually migrating less quantization difficulties. So when we quantize, the quantized weight will be easy and quantizing activations will be hard. So the orange line and the red line, which is W16A8 and W8A8, which means the 8-bit weights, 8-bit activation, or 16-bit weights, 8-bit activation, all fails. So in these experiments, we use 0.5, but this can also actually motivate our research, future research. It actually motivate a lot of future research because in some scenarios, people just want to quantize the weights and not quantize the activation. So people are using this smoothing idea by reversely, they are migrating quantization difficulty from activation to weight, from weights to activation, so they can quantize the weights and keep the activation in higher precision, which I will introduce later. So here is the final system implementation of SmoothQuant. So here is a transformer block in all these large language models. And on the left is the attention module. On the right is the feed-forward neural network. And we replace, originally people are doing this in all of them in higher precisions, like 16-point, 14-point numbers. And now we can replace these computational and also memory intensive modules such as the linear layer, QKV projection, and output projection of the attention, and the fully connected layer FC1, FC2 into integer operators. And also these layers input are quantized into 8-bit integers, which is the green line. So that's actually showing that we are using 8-bit integer matrix multiplication to accelerate these inference. So, but we keep the layer norm and the softmax functions in higher precision because these are not computation and memory bounded, but they are very sensitive to the quantization error because they have some exponent operations and division in these modules, and we keep them in higher precision. And we extensively test the SmoothQuant on, by that time, the largest openly available LLMs. And before SmoothQuant, all the quantization methods failed because they yielded random result. And we can have the comparable accuracy after int8 quantization comparable to 16-bit 14-point numbers on OPT 175 billion. Bloom 176 billion, and GLM 130 billion model, and that's the accuracy on Lambda. And while I omitted all the other baselines because they yielded random results, almost zero accuracy. And on the right is the efficiency. So previously, as I mentioned, although people can serve the 175 billion model in 5 GPUs, but people usually use 8 GPUs. So we can reduce that into 4, so we have better latency. Also, we are halving the memory footprint, but still have the same quality. And we also tested the SmoothQuant on the largest model we can get. So NVIDIA people gave us the 530 billion model, which is the MTNLG 530B model, the biggest model by that time. And we tested and shown that SmoothQuant can also quantize that model with comparable accuracy compared to the 14-point baseline. And also previously, when people are deploying this model, they have to use two cluster nodes because this model is so big and they need at least 16 GPUs to serve this model. And now combined with SmoothQuant, you can serve it with 8 GPUs and reduce the nodes into one and still have same latency. You're having the memory, having the GPU numbers, but have same latency, and also same quality. And later, after SmoothQuant paper is published, we have the famous Llama family model, and we also tested SmoothQuant's performance on Llama. So here is a result. Here are the results on the Llama family, Llama B1 family, and we tested on the Wikitext dataset, which is the language modeling, And these values are the lower the better because they are perplexities. They are measurement of the language modeling ability of models. And as you can see that smoothcon slightly increase the perplexity, which means that this model is still damaged a bit, but still comparable with the original floating point baseline. So smoothcon has been widely adopted in NVIDIA, also in Intel, and also other big companies. So they receive a lot of attention. So this is the smoothcon part. I will pause a bit to take questions. Yeah.
Some cases doctors look for accuracy on some benchmark. You explain a little bit about like why you think that happens.
Yeah, that's a very great question. So we observe that not only in smoothcon, but also in almost all neural network compression techniques. So people, when they prune the network or quantize the network, they find on some benchmark, the performance increase a bit. So and there are several hypotheses, but they are not proven. So you can view these quantization or compression techniques as a regularization where the model is overfit to some data points, but while you are quantizing model and damage the model a bit, it's like dropping out some weights, and then the model will excel and generalize better. So there are literature researching on these problems. Yeah.
So it appears that obviously there are implications for the amount of memory that you need to train and perform inference as well. Or sorry, just inference. But are there implications on latency? Variable inference?
Yeah. So we showed the latency in this figure. So on the left bar chart is the latency where we decrease compared to the FP16 baseline, which is the gray bar. Our method, which is the red bar, decrease the latency. Yeah.
So when you're talking about the outliers of activations, the meaning of this definition of this outlier is saying that it just happens on extreme ends of the integer range, right? It's not outlier in terms of how frequently they happen.
Yeah, so outliers means they are 100 times bigger than the majority of the values.
Right.
Yeah.
Did you also see how frequently they occur in applications?
Yeah, that's a great question. So usually they consist less than 5% of the total number of activations.
Then what is the advantage of computing all that smoothing techniques over just clipping them into a specific number?
Yeah.
If it's happening like less than around 5% of the time, I wonder how much that will actually impact. And
yeah.
The trade-off of actually computing all that smoothing will be, I presume, pretty large. So
yeah.
For the benefits.
Yeah, I don't understand. That's a very great research question, actually. So before smoothcon, people have already proven that these outliers, although they only consist a very small fraction of the total activation, they actually play an important role in neural network. So if we randomly prune like 5% of the values in the activation, the neural network performance will like barely be impact. But if we remove the 5% of the outliers or only 1% of outliers, the entire model functionality will be affected. So these values are actually pretty important. Okay, thank you.
I'm just curious, like, because you have already the quantization for let's say x0, and then got like the activation. So if like there are some outliers in activation, would that cause some overflow to quantize data structure?
So I try to understand this question. So you are asking about am I doing smoothing after quantization?
Yes, like I guess.
Yeah. So there are three stages in smoothcon. The first stage is calibration stage, which we collect the scales, which is in floating point. So we haven't quantized the model yet. And second stage is smoothing stage is also performed in floating point, which is not quantized. And we only quantize the model after smoothing, which we deploy the model.
So those offline exactly.
Yeah, it's not like training because it's extremely cheap because you're actually just running inference and collect the intermediate values.
About LLMs that to have systematic outliers.
Yeah, that's a great question. It's also an open problem. So people still don't. I don't think people still can very confidently understand why these outliers emerge. But there are research paper trying to understand this, and they find out that maybe it's due to the Adam optimizer, where you set the beta 2 to some value like 0.95. They will cause the update in the last forward pass to impact this forward pass. And if some wrong gradients is accumulated, it will drive some channels to bigger values. Yeah, and I also have some hypothesis that because these networks use a residual connection, so actually these channels are pretty limited in its own channel, and they can reinforce themselves through the layer in the forward passes. So, but I don't think there is a definite conclusion on why this happened, and people are still using language models with outliers nowadays. And also there are some I remember there is also another hypothesis says that it's because the softmax makes these outliers, where softmax will enforce all the contextual tokens attention values sum up to 1. So the model needs to increase use some channels as the outliers to perform as some sink or to reduce the entropy of the softmax. So there are some hypotheses, but I don't think there is a definite conclusion on this.
How sensitive is your approach and more generally these kinds of quantization approaches to the choice of calibration data?
Yeah, that's a great question. So I will cover that. That's actually a benefit of SmoothCon and AWQ, and which I will discuss in AWQ later. So in general, it is not very sensitive to calibration data because we are just collecting the maximum value in these activation matrices. It's not data dependent. So I've tried to ablate on this. So I replace it with some code data or just some random input, some random tokens. So in SmoothCon, random tokens even works. So I can recover the model performance by using random tokens to calibrate the model. Yeah, but usually people just use some calibration data from the pre-training corpus, like a pile, like 500 sentences from pile, and to collect the activation ranges.
Yes, so another question. So I'm wondering whether changing the activation function maybe can sometimes reduce the problem of the outliers. For example, I change the remove function to another switch activation function. Does it maybe help to reduce the outliers?
Yeah, that may reduce the outliers. Yeah. So anything happening in your network is like a black box. Even changing one component can changing the distribution of outliers. And we were doing research by that time on OPT models. So here is a visualization of the OPT model, and the follow-up work of OPT is Llama model family, and where they use switch GLU activation function, and also they use row position embedding instead of absolute position embeddings. And in Llama, they can still find these patterns, but it's not as big as this one. And also they have some different intriguing distributions. So yeah, I think replacing the activation function may help with this outlier issue. Yeah.
Is there some information about the best combination of the activation function with the consolidation method? So for example, maybe find maybe for specific models, so which combination of the activation function is the best for this kind of consolidation method?
Yeah, so I think in traditional neural network compression literature, people have developed and get some conclusions because these are CNNs and very easy to train, that you can test and enumerate over all activation functions. I don't exactly remember the conclusion, but they definitely develop some activation functions. But in large language model era, training one large language model is very, very expensive. So people don't have the budget to enumerate these activation functions. And also, people care more in the pre-training stage, people care more about the performance, which is the loss curve. So they will try their best to use the activation function like switch GLU or better activation functions to maximize the ability of the model instead of maximize the model's their quantization friendliness. Yeah.
Should one, but that will be around after. Okay.
Yeah. I will leave some time after this lecture. Yeah. Yes, so let's move into the third topic, which is weight-only quantization, where I will introduce AWQ and TinyChat. So a question to ask is 8-bit weight, 8-bit activation quantization enough for deploying large language models? And our answer is no. So in this figure is a roofline model we get from the RTX 4090 GPU, which is very common in the desktop configuration. So a roofline model shows that if we increase the computation intensity, can the relationship between the computation intensity over the performance of the hardware. So computation intensity is an architecture concept where one element, how many operations we perform on a single element. So in extreme case, if, for example, in matrix vector multiplication, we only load value once and compute it once, and after that we throw it away, then the computation intensity is low. But if we do matrix multiplication, and since after we loading one value, we are using it for the entire row of the next matrix. And in that case, the computation intensity is high. So in this study, we use the matrix multiplication as an example to do this roofline study. And so you can regard the x-axis as the input batch size. So we are studying how the GPU will be saturated, how the GPU will perform when we increase or vary the input batch size. And we can actually see a clear demarcation point as the batch size equals to around 80. So this means that if the batch size is lower than 80, then it's actually doing weight-only quantization is better than doing both weight and activation quantization. And when the batch size is larger than 80, since the input size is very large, so we can use the int8 tensor core to accelerate the computation, and also we can use int8 to decrease the weight size. But when the input is not big enough, actually what dominates the overall latency and the performance of GPU is the memory bandwidth. So quantizing the weights into lower bits, such as 4 bits, and keep the computation in 16 bits will actually give you a higher throughput, because the entire workload is dominated by the weight loading instead of the computation. So W4A16 means that we quantize the weight into 4-bit, and we load the 4-bit weights into some high-level memory or registers, and we convert them into 16 bits and perform the computation in 16 bits. So W4A16 doesn't accelerate computation, but it accelerates memory loading and memory traffic. So this actually gives us intuition that in edge devices where we want to deploy language models on your laptop or on your cell phone, since we don't have a large batch size, we only have one customer to serve, which is yourself. So that's batch size equals to 1. Then we want the weight-only quantization instead of the weight activation quantization. So we can actually break down the large language model inference into 2 stages, which is the context stage and the decoding stage. So in autoregressive language models, people usually input a very long prompt into the language model, and the model will encode the prompt, which is we call the context stage. And then the model will do autoregressive decoding to generate each token, which we call the decoding stage or generation stage. The model do the token by token generation. So at the first stage, it's actually pretty saturated because it has you input a lot of token into the model, and the model is doing matrix multiplication, so the computation intensity is high. So it's better to use weight matrix multiplication to use W8A8 smooth square quantization. But during the decoding stage, actually, the model itself is actually doing matrix vector multiplication, since you are only inputting one token at each forward pass. And that process actually mainly dominated by the memory traffic. And we can actually break down the memory traffic into two parts. So we break down by wait traffic and activation traffic, which is shown on the right bar chart. So as you can see that we can actually intuitively understand that why the wait memory footprint is far larger than activation memory footprint, because in language models, the large language models, the model weight itself is very big, and the input, when we are only inputting one token and decoding one token, the activation is far less than the weight. So actually, this motivates us to push further on the weight compression rather than compressing the activation. So we start our experiment on a very simple variant, which is called the round to nearest quantization method. So round to nearest is just we use 4-bit integer to quantize the weight and keep the activation in 16 bits, and we just naively quantize the weight matrix and map them into the nearest quantization level. And in extreme cases, like 3-bit quantization, which is shown on the figure on the right, we use OPT 6.7 billion model and show the perplexity, which is the lower the better. And while we are using run to nearest, the model performance suddenly breaks. So we can see that originally the model have a 10-ish perplexity, and now it has 40-ish perplexity, which means that the model cannot be used in real world cases. And but we find out that if we smartly select some of the columns, some of rows in the weight and preserve their precision. For example, we keep the second row untouched and only quantize all the other rows. And we can see that by only keeping those 1% of weights, we can hugely reduce the perplexity and recover the model's performance. So here is a natural problem to ask, which is a question to ask: how can we find those channels, which we call salient channels in weights? And should we select these channels based on weights or based on activation, or just randomly select these channels? And actually, this turns out that this selection strategy plays an important role on the accuracy of model quantization. So previously, when people think of if we are going to do some operation on the model weights, we have to focus on the model weights. For example, in pruning literature, people find out that larger values in weights are important and smaller values are not important. So we want to prune the smaller values, and also in quantization. But in our study, we found out that a very interesting situation is that if we quantize if we only preserve the weights based on its magnitude, then it's similar as randomly selecting the channels to preserve precision. However, we did another experiment where we look into the activations of the large language models, which is the X matrix. So as we discussed in the SmoothQuant paper, we find out that there are channel-wise distributed outliers in the activation of the large language models. And if we check which column is the outlier column, and we preserve the accuracy, we preserve the precision in weights of these rows, then we can hugely improve the perplexity and recover the model's performance. So this gives us, so the biggest takeaway in this slide is in large language model weight-only quantization, we should not look into the model weights, but instead we should focus more on the model's activation. So, however, this introduces another question. So we finally, now our algorithm is to we check the activation distribution and we find out those outlier channels and we keep those outlier rows in the weights into higher precision. But however, in real world GPUs, this is not real world hardware friendly because we are keeping some of the numbers in the entire matrix into higher precision and quantizing most of the values. So actually we need two kernels in each matrix multiplication because we need one higher precision kernel and one lower precision kernel. And also we need to reorder these channels so that these channels are continuous instead of scattered around. So if they are scattered randomly in the matrix, we need another scatter and gather operation to get these higher precision rows out. So that will incur other overheads. So here's a question. Is it really necessary to introduce mixed precision for weight only quantization? So the answer is fortunately no. So we have method to avoid mixed precision. So we developed a method called protecting the salient weight by scaling. So the idea is actually very simple and it's inherited from smoothQuant. So after we identify the channels by the activation magnitude, we can actually we are able to scale up these channels. It's not just scale. It is not scaling down, but scaling up. So you can imagine that we identify some of the values in the weights, which is very important in order to preserve their quantization and quantization precision and not reduce the quantization error. We want these channels to as big as possible. So we scale up these channels and scale down to preserve the mathematical equivalence. We need to scale down the in the activation side. And in this figure, we can see that while we are scaling up these salient channels by 1.5x, we actually hugely reduce the model perplexity. And while we are push further, increases by 2x, and we are actually improving the perplexity further. But if we further multiply these outlier channels, then the model perplexity goes up again. So can anyone explain why that happened? Sorry.
I'm not sure whether it's overfitting problem. So if you want to maybe give more precision to the outlier channels, so you will cause overfitting, I think.
Yes, that's a good hypothesis, but it's not the cause. So the cause is that we are actually scaling up some of the channels that previously not the maximum value. But if we are scaling it up too much, they become the maximum value. And after that, we are actually increase the quantization error of other channels. So previously, while we are scaling up this channel, they are not affecting the overall maximum value of the entire matrix. But to a certain extent, it becomes the maximum value in the matrix, and it will cause the matrix to have larger quantization error. Yeah. So it's very important to determine which value we are going to scale up, which extent we are going to scale up these channels. So we want to understand why this happened. So we did a error analysis on this problem. So here is the equation of the quantization formulation, which I introduced in the first part of the lecture. So I just replaced the scale to delta because sometimes people represent it by delta. Sometimes in the paper we write delta. And delta is the quantization scale, which represents the step length of the quantization level in the quantized range. So originally, since here we are only quantizing the weights, so the only error we can get from is the rounding function, which is the round W over delta, and X and delta is all floating point numbers, so there are no error in this. So when we are scaling up some of the weight channels, we actually increase some of the weight values. And if we are not affecting the entire weight's maximum value, for example, we are only increasing some weight's value and it's not becoming the maximum value in the weight matrix, we are actually not affecting the delta. because delta is purely determined by the maximum value in the weight matrix. So here the arrow is only coming from the rounding function. And since the weight matrix distribution is very random, so we can have an expectation that this rounding function has a arrow of expectation of 0.5. So no matter how you no matter what the input will be, as long as they are not entirely on the one side of the quantization level, this rounding function will have a expectation of 0.5 relative error. And by increasing the salient weights channel, we are actually reducing their relative quantization error, because since the absolute quantization error will be 0.5, sorry, it's absolute quantization error. By increasing these weights, we are actually reducing their relative quantization error. And here it shows that our method can, so here we discuss how can we get the scaling. So we are actually determining the scaling, how much we are going to adjust the weights by looking into the output activation instead of the weight, also instead of the weight. So here the loss S is the function we want to optimize, which we use some binary search to optimize this function. We want to search the optimal S to minimize this function. And finally, we get the smoothing factor, the scaling factor to increase the weight matrix channels. So in the end, we developed the AWQ algorithm, which is very accurate, very simple, easy to implement, and it also has a good hardware efficiency because it never used mixed precision in matrix multiplication. And also we show that this has AWQ algorithm also has less dependency on the calibration data set. So here is on the right-hand side is a table where we show that when we calibrate the model with different calibration data sets like PubMed and Aaron, and we test the model's perplexity on PubMed and Aaron again, and we by comparing with the baseline called GPTQ, we can see that GPTQ actually overfit on the calibration data set, because while we are calibrating on one data set, it has terrible performance on the other data set. But AWQ has better like insensitiveness to the calibration data set, and it will not overfit to the calibration data set. Yeah, also AWQ has a good result in terms of general natural language understanding benchmarks, and it reduced perplexity compared to even a very strong baseline like GPTQ with reordering, GPTQ-R. And we also show that GPTQ can optimize the visual language models and compress visual language model on device, which is very important. We want to deploy visual language models like Lava or Vila, these models on your device, on your phone, so you can do interactive and visual chatting with them. So we show that AWQ can, by using only text calibration data sets, we can calibrate the vision language model and quantize them into 4-bit. And we have several interesting demos on these websites. So they are very useful in real-world cases where we can interactively use a phone and run some visual language model and do visual question answering. And here is the VLM result by using AWQ. So we can see that as the student asked before, on some benchmarks, we can even have better results compared to the baseline, such as MMWet, we have better results. So AWQ also has a significant industrial impact, and it has been downloaded a million times on Hugging Face, and has been integrated in a lot of platforms like TensorRT LLM, Hugging Face, and VLM. Yeah, that will be the AWQ part. So I can pause here to take questions. Yeah.
You presented a table where you compared the quantitative results after applying AWQ.
Sorry, which slide?
This one. like the next one. Yeah, so I noticed that the very minor difference in the quantitative. Did you also observe any qualitative changes in the?
Oh yeah, so I didn't include it in the slide, but if you Google the A.W. Cook paper, there are several qualitative examples in the appendix. Also, you can check this website. I think they are still hosting it, so you can view the demo as a qualitative example. So you can just test it real time to see if the quality is favorable.
Was there like any noticeable trends in the qualitative?
Yeah, so basically what we show in the paper, it must be good result, right? Yeah, and usually if you do that, there will be no noticeable differences, but still the model output will change because you are changing the model weight. Yeah. Yeah, any further questions on this? Yeah, okay, so I will move on to the advanced topic, which is our recent work is called QServe. So we want to combine the benefits from SmoothQuant and A.W.Q, combine the benefits from both worlds and propose a method that can not only compress weights, but also compress activation so that we can accelerate inference by using integer kernels. And in the end, we developed a W4A8 KV4 quantization method, which is 4-bit weights, 8-bit activation, which also means 8-bit matrix multiplication. And we also quantize the KV cache in the GPT models into 4 bits. So that means that in long context scenarios, we will have used less memory. So we still began our analysis through the roofline analysis. So the right figure show the A100 roofline model. The A100 has a DRAM bandwidth of 2 terabytes per second, and the peak performance of FP16 Tensor Core is 312 TOPS. And that's so using the int8 kernel actually gives us double the TOPS, which is 624. So for cloud serving purposes, the typical setting nowadays is using the SmoothQuant, which is W8A8 setting, and for edge devices, people are using A.W.Q. And this is all we introduced in previous slides. But what we are thinking is, can we use 4-bit for weights and also 8 bits for activation so that we can have a strictly better roofline model? Because not only in smaller batch size settings, but also in larger batch size setting, we can outperform the WAA8 and W4A16 methods. But unfortunately, the existing method failed because implementing 4-bit models is very 4-bit method and matrix multiplication is very costly and has a lot of overhead. So here is a figure showing that while there are 2 baselines called Atom and Quarroot at that time, which implement W4A4 kernels to compress the model. And what we show that their method actually have a terrible throughput or latency on the A100 GPU is because their method includes some rotation and some mixed precision implementation in their method. So they cannot fully leverage the potential of the hardware. So they cannot run efficiently on the GPUs. And also we show that directly reducing the KV cache into 4-bit will significantly degrade the LM accuracy. So here is a visualization which is similar to SmoothQuant, which shows the value and the keys of the activations of the language model. So in attention mechanism, people will compute the QKV query key values, and people usually accelerate decoding by hashing the previous keys and values so that we don't have to recompute them during the decoding stage. And we want to cache those keys and V and also compress them so that we will reduce the storage requirements of KV cache. But quantizing the keys and values are not simple. So values are very easy to quantize, which is showing that they are flat and uniform. But quantizing the keys are not very easy because there are several outliers. And what we propose is pretty similar to smoothquant. So since we are not quantizing the query because they are represented by 8-bit, so query has larger bits, bit width. So we only want to quantize the keys and values into 4 bits, so we can migrate the quantization difficulty from keys to queries. So in attention computation, it does matrix multiplication of keys and values, which is Q multiplied by K. And we can do a similar transferring, like magnitude transferring process like smoothquant, where we migrate those outlier channels into the previous queries. And in our practice, we find that we still use the smoothquant alpha equals to 0.5 setting. So we collect the maximum values in each column and migrate it into the previous layer. So after smoothing, we can see that the scales are hugely reduced. And there is another technical detail which is due to the application of the rope precision encoding. So language models are using precision encodings, and a very famous, widely used language precision encoding is called ROPE, rotary precision encoding, where they encode, they put precision information in the keys and queries of language models. And since during the precision encoding process, they have to usually pair some columns to insert some precision information. So we add a constraint that we limit the index I to have the same transferring migration as the I plus D over 2. So that's a technical detail we are using. And we do the rotation and smoothing in all the layers of transformers. So on the top, which is the rotation illustration, we add rotation to the to 2 consecutive layers, and which is represented by the rotation matrix Q. And to study rotation, you can refer to a literature called Quarut, which is basically it's like smoothquant. You add some mathematical equivalence operation between 2 matrices, but this time it's not a diagonal matrix, which is the per column scaling. Now people can add some small hard rotation kernels, and so that you can further reduce the quantization difficulties, but with slightly increased overhead. And here is rotate. We also do layer-wise rotation and layer-wise smoothing to further reduce the outliers. And finally, another technique is called activation-aware channel reordering. So in AWQ, we find that maintaining the salient weight in 16-bit floating-point numbers can significantly improve model performance. But we want to quantize the weights, so to further reduce the quantization error. So a better practice is to put these salient weights into a same group, because we are using group-wise quantization. So we are not quantizing the entire matrix into one using one quantization configuration. We are actually grouping those weights into subgroups, and for each group we use a 0.0 and a scaling factor. So we want those salient weights to use the same quantization configuration, because they are all very big, and we actually achieve this by reordering the weight channels. So we have an input X, and we can identify which input channel is a larger channel, and we collect the absolute maximum value, which is shown below, which is the yellow vector. And then we reorder the weights by the sorting index obtained in the activation vector. So finally, we clustered those salient weight channels together, and so that they have better quantization, and we can reduce the quantization error. So by combining these techniques, we further pushed this frontier. So we enabled W4A8 quantization on various model families, including Llama 2, Llama, Mistral, Mixtro and E model. And we further pushed down the quantization, we further pushed down the perplexity. And here is the, sorry for the title. So here is the system implementation of the QSERV model. So compared with smoothquant, we further reduce these linear layers and KV cache into 4-bit integers. And also the input of these layers are 8-bit numbers, so that we are actually using 8-bit matrix multiplications. And we still keep the softmax and layer norm layers in 16 bits floating point numbers. So here is the end-to-end throughput evaluation result. So we can compare to the industrial state-of-the-art inference platform, TensorRT LLM. We can achieve up to 2.4 to 3.5 faster throughput. And also we beat the two quantization method, Atom and Quarut, which is using W4A4 quantization mechanism. And here are the throughput measured on other models, which also we show significant speed up. Yeah, so this will this conclude my talk. So today we talk about the basics of linear quantization, and we go through two types of quantization schemes: weight activation quantization, which is smoothquant, and also weight-only quantization. Weight activation quantization is useful in cloud serving scenarios where batch sizes are big, and weight-only quantization is very useful in edge devices where we push the model, compress the model weights further and perform inference in higher precisions. And we push further by combining these techniques, and by proposing some further optimizations, we enabled W4A8 KV4 quantization in QSERV. Okay, thank you everyone for listening. Yeah.
Very general question. Do you have advice for anyone who is trying to be, to get started in research in this area?
So in quantization or efficient machine learning?
Quantization.
Yeah, I think from my experience, I think get hand dirty is very important. So I started playing with these models, but without knowing a lot of concepts. And I think when I was a first-year PhD, I observed this phenomenon. So actually, I propose a very simple method. The smoothquant is a very simple method, but previous people hasn't proposed. And I think the secret and what benefits me most is to get hands dirty and to very carefully observe the phenomenon in these models. So I started to analyze how these outliers distributed and why they are causing the model to fail. And by visualizing these outliers, I find out that they are actually distributed on certain channels. So that came the question and the solution. So I think the secret is to get hands dirty and look into the model itself. But also, I think identifying the problem is also very important. So back then, I think I have a intuition that quantization is a must to deploy those models because they are so big, and it's like a free lunch to decrease their memory size and also the computation precision. So yeah, I think these two are some suggestions.
Research to start with for the student?
Yeah, so I think basically doing inference is not that costly. So nowadays we can on A100 GPU, you can, if you do inference in 16-bit floating point numbers, you can handle all the models below 30B, right? So doing inference only research is not that hard. And the other suggestion is maybe you can do internship at the industry in the industry, so they have better resources. Yeah, and for training research, I think they do need more resources, and I think maybe start off by using PEFT method, like parameter efficient fine-tuning to explore your idea, maybe a good starting point. Yeah.
Okay, so I think it shows, so the outlier lies in single channel. So is there any scenario that so the outliers are spread across all channels?
Oh, so you're talking about if we are making the previous layer harder to quantize.
Yeah.
Yeah. So in this case, yeah, this is a good question. So we're quantizing the previous layer's output, which is the Q, in 8-bit integers, but we want to quantize this keys into 4-bit integers. So previous layer had more effective bits, so it can tolerate more outliers. Yeah, but it does make the previous layer harder to quantize. Yeah. Yeah. Okay.
So you asked me whether my question was about quantization or efficient inference. So now can you answer the question for efficient inference? How does one get?
Yeah, I think maybe starting off by reading literature. My advisor has a course at MIT, which is the TinyML and efficient machine learning computing. So maybe start off by reading some course materials and starting off by basic ideas like pruning, quantization, distillation, and combining these concepts and may understand well in the most important question in this field, I think.
Including like entire end-to-end computational efficiency. Is there a reason you didn't include like pruning techniques, structured pruning or unstructured? Can you guys speed that up?
Yes, so the topic of today's lecture is quantization. So I include 3 works from our lab to demonstrate that, but definitely structured pruning and pruning is important, and there are good research and study on that. Yeah, so maybe the research work like Wanda, shared llama, Minitron, they are good examples of how pruning can increase the efficiency of large language models.
A lot of this talk has been about like efficient inference. Could you tell us a little bit more about how this work would relate to like taking that step further and going to fine-tuning?
Yeah, so fine-tuning model. So there's a great method called QLoRa, where people use the base weight as quantize the base weight and only keep the LoRa branch, which consists only minimum fine-tuning values in higher precision. So QLoRa can hugely reduce the requirements for fine-tuning. And so basically you can combine all these quantization techniques in QLoRa and only fine-tuning only keep some values in higher precision and keep most of the values, frozen values, in integers.
Is the preservation of the performance of quantized models depend on the downstream tasks? So if you quantize a model, it's constructed and trained to do classification. Does like quantization is still effective in those cases?
Yeah, so that's a great question. So in the pre-LLM era, there are task-specific concepts where people train different networks to do different tasks, and they train on specific tasks. So in these cases, using domain-specific calibration data is very important to make these quantization performance better. But now in the LLM era, people tend to use one model to do all kinds of tasks. So actually, the model are doing all kinds of tasks itself. So we already showed that the method we propose, smoothquant and AWQ, actually are pretty insensitive to the calibration data. And a hypothesis is that the model itself is actually just decoding tokens, and it's basically doing the same task over and over again. So if your So if you design good quantization method and it's not overly dependent on the data you use, such as you're not doing fine tuning on the data, but you're collecting some statistics and doing calibration, then it will not depend on the data a lot.
Is there a way to prevent these outliers from creating?
Yeah, I think I discussed that question previously. So people have hypotheses on how these outliers are emerges. So people have already proposed some regularization to reduce these outliers. So you can imagine that most brute force method is to add some regularization to penalize those outliers, but they have effect on they have some negative impact on the model output. So people. So as I discussed before, people want to maximize the model performance, so they actually don't care if the quantization difficulty is increased at the pre-training stage. At least this is not their first priority. Their priority is to make the model as powerful as possible. So yeah, there are some techniques like replacing the attention or setting the second term in the Adam optimizer to like 0.99. And other alternatives. Yeah, but I think the biggest issue is that during pre-training, people's first priority is not to ensure its deployment efficiency.
Training stage. So, incorporate some optimization function that's like use a large language model that is easy for optimization.
And so you're talking about can we add some training techniques to make the model easier to deploy? Yeah.
So I believe like in the original like LLM training architecture, there are only optimization targets or like the better accuracy. Is it possible that at the training stage you can train such a large language model and certain properties that is easier for this optimization and deployment?
Yeah, so I think there are. So there are some rumors that big companies are using like quantized model to train from scratch so that the model is naturally quantized while it's deployed. Yeah, there are techniques like these.
Let's end the speaker.
Thank you.